Let's continue in 1.4, solving systems. Let's look at another important concept, and basically what happens if you have a row zero out completely. So let's talk about this form here again. You have your augmented matrix, coefficient matrix with your constants, and then you do all your row reduction, and you get down to this form. So this, basically we're going to look at these types of theorems and properties. If this is the identity matrix, then that's a unique solution. But what if it's not? What if you get like all zeros in one row or something? Then how do you handle that? So let's talk about that. So let's look at this example like this. So this is actually as if it was already reduced, like what happens. So suppose the system AX equal B yields the following. So you have some system, you row reduce and all that. So suppose you had A augmented with B. I guess that's a vector. And then you do your row reduction and you get H and then C over here. So you do that process like we just did. And let's suppose you end up with this augmented matrix. You get 1, 0, 1, 2, 0, 1, and this ends up being negative 1, 4. And then this row zeroes out, 0, 0, 0, 0. So if you get something like that, then always keep in mind you have X, Y, Z, and your constant. And so the last row we want to consider as your Z variable. So think of it as X, Y, Z. And so basically what we have is 0, Z equals 0. So Z can be any number. So that statement is satisfied if Z is anything. So Z, I'll write it out in words right now, can be any number. So coming back up here, so what we say then is we'll let Z be a real number. Oops, I totally wrote that wrong. Let Z equal T, which is in the reals. So you're letting it be arbitrary. So then what you get is when you back substitute, you get your different forms. You get Y minus T equal to 4. And then you can solve for Y in terms of T. So Y is T plus 4. And then similarly, you have X yes, okay, I was looking at the wrong one. So yeah, so this is your Y right here. This one was Y minus T equals 4. So now I have X plus T equals 2. So X plus T is equal to 2. And then we can solve for X in terms of T. So X then would be T plus 2 or negative T. So it would be negative T. I put that first, plus 2. And then Z is T. So that's your system. So you can split that up and break that up into this form. So my let's call it C, I guess. So C, because that's what this is basically. Sort of. That doesn't matter. So C looks like this. Here's your X, Y, Z as a column vector is equal to negative T plus 2, T plus 4 for Y, and then just T. And then we can basically break that up into a sum of two vectors. So that we can say is equal to negative t, t, and t. This will be a typical thing we do when we break this up. Plus, and then this is 2, 4, 0. Like that. And then we can even factor out that t and have basically negative 1, 1, 1. And then t is your arbitrary value on the outside, like that. Plus 2, 4, 0. And so we end up with this form we will talk about a little later, but this is the xh plus x particular. So this is called your homogeneous solution, and this is your particular solution. What we have, some more terminology is we say that we have one free variable. And depending how you solve it, it doesn't really matter the free variable. Usually when you do the row reduction, it becomes your z, or it could be the next one. So if you end up with 2 rows 0 out, then you end up with 2 free variables, and you have 2 arbitrary constants. So let's look at that, another example where you have that. So let's change back to white here. So you have, this will be 2 free variables. Okay, so same type of question. Suppose ax equal to b yields the following. So you get a, so same thing, a augmented with b, you do your equivalent row reduction, HC, and this time you get this. We're going to use x1, x2, x3 instead because we have 4 variables in this case. So you get 1, 0, 1, 0, 3, 0, 1, 0, negative 5, 2, and then the rest 0 out. And so just this one I put in there, but let's suppose they only gave you this. Then you add the extra rows to make it the proper number of variables, like that. Okay, so you add rows to include your free variables, and you'll see homework like that. So this is the system, and they might have done it on this one, but I forget where I get this one from actually. So what we then have is x1, x2, x3, and x4, and then those are your constants. So this means that 0x3 is equal to 0 and 0x4 is equal to 0. So now you have 2 free variables. So x3 and x4 are your what we call free variables. So let's let x3, so you just got to pick two constants. You picked s and r this time. So let's pick s3 or x sub 3, x3, to be s, which is in r. I'm not sure why I picked it up. Yes, we'll just stick to my notes so I don't mess it up. And then x4 to be r. Usually you would say like QRS. Anyway, alphabetical, doesn't matter. Okay, so that's what we're going to do. Those are my variables. Those are my arbitrary variables. Now back substitute with r and s. And I'll write that out this time to keep us clear on what's going on. So now back substitute just replacing or substituting with RS. You get the idea. So you get, so this is what you're using here. And you could write that all out. I'm just going to go ahead and substitute. So you get x1 plus s equal to 3, x2 minus 5r equal to 2, x3 is s, and x4 is r. Now let's write that in a better form. And so you get x1 is 3 minus s, x2 is 2 plus 5r. And just basically, right, I'm just substituting in right there and just setting it equal. And then now I'm solving for each variable. x3 is s, and x4 is r. And then let's write it in that other form. And I'm going to do it in one page here. So let's bring this over. I'm going to bring this over here, and then we'll simplify a little bit. Just better for the videos to get it on more on one page. So we get x, and well, in my notes too, I guess, if I was teaching this in class. So you get x1, x2, x3, x4. And then now write that in the same format. It's 3 minus s, 2 plus 5r, s, and r. And then you just simplify it. This is called your general solution. I forgot to write that up there. So 3 minus s, 2 plus 5r, s, and r. Okay, so that's your general solution. And what you can do, and I didn't really mention it back here, but if you choose, so since s and r can be anything, or t in this case up here, you can choose values for r and s and then just get what's called a particular solution. So in this case, even if you zero everything out, you do not get just the trivial case. So not the, but a particular solution. So there's an infinite number of solutions, obviously, right, for R and S. So what we call particular solution, we can let R and S be 1 or anything really, right? So R and S be 0 in either case. So you can get X particular. So if it's 1, then you get 2, 7, 1, 1. And then if it's 0, notice I say X in the subscript particular there. This case over here, you get 3, well, you get 3, 2, 0, 0. So you can, another particular solution. It's like saying, here's a point or a vector on the line or something. Be like that. And we can break this up as well into that other form. So I mean, I can probably fit it right here. So the general solution, we could simplify this and then say this is equal to essentially this vector 3, 2, 0, 0, and then plus -1, 5. Oh, this one you have to do separate. Yeah, okay, we'll get to this later. Okay, you know what? Let's stop there. We'll leave it like that. That's the general solution. So sorry about that. You have to break it up with R and S separately, which I have plenty of more examples once we get going on more of these concepts. Okay. I think that's it there. Now we need to move on to Well, you know what? I better do it just in case. So let me show you how to do this. So let's copy that. I'll just do it down here. So what you can do for something like that is you can say this is, you get 3, 2, and then 0, 0. Right, you break that up. And then the first one is just S. So you're going to do S, and then you're going to do a product. And then you're going to have another one with just R. And so this one will be a -1, and then this nothing in the second position, and then 1 and nothing in the third. So you picture multiplying by S and then adding. Same thing up here. This is 0. This was R right there. R is there. And 0, this has to be a 5. And next one 0, and next one 1. So if you multiply in, you get nothing, 5R, nothing, and R. Added to this one, -S, nothing, S, and nothing. So when you add them up, you end up with this form. So that's how you can break it up. And we will talk about dimension, essentially. We'll talk about there's two free variables, your R and your S, R and your S, and these vectors being representing the space of the matrix. So we'll have what's called a row space, column space, and null space. And that's what this type of format has to do. And whether or not these vectors, when you do their linear combination, make up the whole space. We get into that concept. So it gets a little ahead of where we're going to, but that's the type of thing we will be doing. Okay, so now I think that's all. So now I think we're done. Yeah, that's all we needed for, oh no, one more thing. Okay, so I mentioned this. Let's go ahead and define it so we have not another video. So there's more practice on row reduction for sure, but let's do this definition for span. So just practice more row reduction. Let me write that down. No, that's not going to show up. So practice more row reduction. Takes a little effort at first, and you have to be okay at it. You have to be, don't make a lot of mistakes and be okay at it. You don't have to be hugely proficient at it, but just know how to do it given enough time, because you have to know how other things operate. Okay, I was going to show you this question, this definition 1.4 is a definition of span. So if you take the span of these vectors, these are vectors v1, v2, etc. to v sub k. So the span of those vectors is what we're defining. And it's basically all linear combinations. So let v1 to v sub k be in Rn, right? So in dimensional space there. The span of vectors, hands in the wrong spot there. So the span of vectors is all possible linear combinations of the vectors, right? Of all those vectors. So you say that this span, oops, do that a little better. We say the span of those vectors is equal to this set. It's the set R1 V1 plus R2 V2 plus etc. all the way to R sub k V sub k. So it's that sum, changing all those vectors around, right? Such that R1 to R sub k are real numbers. These are your scalars. So that's what it means to be a linear combination, right? It's a scalar plus the other vector. So here's a simple example we'll do first. Does, and we'll have more later, but a lot of this you've got to start looking at in homework and reading more of the book. It's a lot here. Does 1, -2, and -3, 6 span all of R2? Meaning, does the linear combination of those make up all of R2? And so if you were to, so it's considering the idea of like I and J. If you span I and J, you get all of R2. We've talked about, right? You do all linear combinations, a scalar plus another scalar, then that vector makes up every vector in R2. Okay? So this one's simple because you can just see that it's a scalar multiple. So if you do 1, -2, that is equal to, well, it's not equal, but 1, -2, then look at, if you just factor out -3, what do you get? You get 1, -2. So, so that's just, it's a line. It's a one-dimensional line. You're getting W is equal to K times V. So it's the same direction, or opposite. I guess it's opposite. But it's basically saying you have a line like this, you have a vector, and all you're doing then is either going longer or reversing the direction. But you can't go in a different angle. Like, it's either same direction or opposite, but not that one or that one or that one. So because they are scalar multiples of each other, so scalar multiples, therefore no, those two vectors do not span all of R2. Okay, so we'll get more into that as we go. 1.5 is inverse matrices, and then that'll take a little bit. And then 1.6 is on subspaces. And that'll be it. It's kind of a lot in chapter 1, huh? Okay, moving along.